I'm Fleshed Out Thoughts, and I love fleshing out thoughts for extended periods of time. And I'm building a full stack e-commerce platform for digital products and software services with Next.js and Supabase. This series is about the architectural decisions behind the platform, what I built, why I built it that way, and what I do differently. Today, we're going to be getting into consistent hashing explained, what it is, why it matters, and when I'd use it. Let's go. There's an algorithm that answers a deceptively simple question. Given a key and a set of nodes that change over time, which node should own that key? It's called consistent hashing, and it is the foundation of distributed caches like Memcached, distributed databases like Cassandra and DynamoDB, CDN request routing, and service mesh load balancing. My platform is a single Supabase instance and a single Vercel deployment right now. I don't need consistent hashing today, but understanding it means I'll recognize exactly when I do, and I'll avoid the trap that causes cascading failures when a cache node goes down. This video is about how consistent hashing works, why the naive approach fails catastrophically, and where you'd use it in practice. The core problem, routing keys. The routing problem appears everywhere in distributed systems. You have a key A user ID, a cache key, a partition identifier, and you need to decide which node in a cluster should own it. A distributed cache needs to know which server holds a cached product. A distributed database needs to know which shard owns a row. A CDN needs to route requests for the same video file to the same edge node. The routing function must satisfy three requirements. First, determinism. Every client asking about the same key must get the same answer. Second, distribution. Keys must spread approximately evenly across nodes. Third, stability. When the set of nodes changes, a node is added, a node fails, as few keys as possible should be remapped to the new owners. The first two are easy. The third is the hard one, and it's the entire reason consistent hashing exists. Why modular hashing fails catastrophically? The simplest routing function is modular hashing. Hash the key, take modulo the number of nodes. It's deterministic. It distributes keys evenly, and it fails catastrophically at stability. Let me show you why. With 4 nodes, you compute the hash key modulo 4. If you add a 5th node, the modulus changes to 5. Approximately 80% of keys now map to a different node than before. With 10 nodes becoming 11, about 91% of keys move. For distributed cache, every key that moves is a cache miss that falls through to the database. Adding capacity to relieve load actually causes a bigger load spike than the capacity addition was meant to absorb. The database, which was sized for a 5% miss rate, suddenly receives 80% of all requests. It falls over. The system degrades catastrophically. This is not hypothetical. It is a well-documented failure mode that has caused major outages. The fix, consistent hashing. Let me show you the difference visually. On the left, modular hashing with 4 nodes. When a 5th node is added, the modulus changes, and nearly every key gets a new arrow pointing to a different node. The remapping is nearly total on the right. Consistent hashing with a ring. The same change, adding a node, affects only the keys on the arc immediately clockwise of the new node. Most keys stay where they were. Only about 25% move, compared to roughly 80% with modular hashing. For a 10-node cluster, adding 1 node remaps about 10% of keys with consistent hashing. With modular hashing, the same change remaps about 90%. The difference is a 9x reduction in disruption. The hash ring and how it works. How does consistent hashing achieve this? The key insight is the hash ring. Imagine the output space of a hash function as a circle. For a 32-bit hash, values range from 0 to about 4.3 billion. The ring wraps around. The value immediately after the maximum is 0. Every node is placed on this ring by hashing its identifier, its host name, or IP address. Every key is also mapped to the ring using the same hash function. A key is owned by the first node clockwise from its position. When a new node is added, only takes ownership of the arc directly clockwise behind it. The keys between the previous node and itself, all other arcs, and all keys on those arcs are completely unaffected. Adding 1 node to an n node ring remaps approximately 1 over n of all keys. That's a guarantee. For a 10-node cluster, 10% of keys move. For a 100-node cluster, 1% move. The stability property is built into geometry of the ring. Virtual nodes. The basic hash ring has a critical weakness. With a small number of physical nodes, the position they hash to the arc are not uniformly distributed. A 3-node ring can easily have one node responsible for 60% of the key space and another for 10%. The distribution is far from even. The solution is virtual nodes. Instead of giving each physical node one position on the ring, you give it many, say 150 positions by hashing its identifier with different suffixes. With 150 virtual nodes per physical node, the law of large numbers ensures each physical node's cumulative arc size converges towards 1/n over the total ring. The variance drops from 30% or more to about 3%. Virtual nodes solve a second problem too. When a new node is added, its virtual nodes are distributed around the ring. It takes its load equally from all existing nodes, not just from the node immediately clockwise of it. This means load shedding is balanced. Every existing node gives up roughly the same fraction of its keys to the new node. Cassandra uses 256 virtual nodes per node by default. DynamoDB uses the same approach internally. Each partition is assigned with multiple tokens, and the number is chosen to balance distribution with overhead. MEMS cached Kitama algorithm uses over 160. A practical default is 150. Distribution quality is good. Memory overhead is negligible. Replication of the ring. Consistent hashing tells you which node owns a key. It does not copy data to multiple nodes, provide failover, or ensure data is available when a node fails. Those are separate concerns that build on top of the ring. The standard replication strategy. Walk clockwise from the key's position and assign it to the next n distinct physical nodes. With a replication factor of 3, each key exists on 3 consecutive nodes. If one node fails, the other 2 still serve reads. If you need strong consistency, you can use a quorum reads and writes. With 3 replicas, a write must succeed on at least 2 nodes, and a read must query at least 2 nodes to guarantee seeing the latest write. The math, R plus W greater than N, guarantees overlap between the read set and the write set. From zero-where placement, you skip virtual nodes that belong to a physical node in a zone already represented in the replica set. This ensures your replicas aren't all in the same availability zone. Where it's used in practice, consistent hashing isn't theoretical. It's deployed inside systems used at enormous scale. Memcache clients use libkitama to route keys to cache server. When a server is added or removed, only a fraction of the cache is remapped. Apache Cassandra uses consistent hashing as its fundamental data distributed mechanism. Each row is assigned to a token based on the hash of its partition key, and each node is responsible for a range of tokens. Amazon DynamoDB uses consistent hashing internally to manage partition. Redis Cluster uses a related approach. It divides the key space into 16,384 hash slots. Keys are mapped to slots, and slots are reassigned when nodes join or leave. The effect is similar to consistent hashing. Only a fraction of the key space moves, but the implementation is slot-based rather than the ring. CDNs use consistent hashing to route requests to the same URL, to the same edge node, maximizing cache hit rate and minimizing origin fetch cost. The algorithm is everywhere. Once you understand it, you see it in every distributed system you encounter. When I'd use it on my platform? Right now, my platform is a single Supabase Postgres instance and a single Vercel deployment. I don't have distributed cache clusters, a sharded database, or multiple backend instances that need session affinity. I don't need consistent hashing today, but I know exactly when I would. If I add a Redis cluster for caching and need to distribute keys across multiple Redis nodes, I'd use a Redis cluster built-in hash slot routing. If I shard my database and need to route queries to the correct shard based on the partition key, I'd use consistent hashing to minimize remapping when shards are added. If I run multiple backend instances and need sticky sessions for WebSocket connections, I'd use Envoy's ring hash load balancing. Understanding the algorithm now means I'll recognize the use case when it appears, and I'll avoid the modular hashing trap, the one where adding a node to relieve load causes the very load spike you were trying to prevent. Consistent hashing solves the key routing problem when the set of nodes change. It guarantees that only 1/n keys are remapped when a node is added or removed, compared to nearly all keys with modular hashing. The hash string maps both keys and nodes onto a circular space. A key is owned by the first node clockwise. Virtual nodes ensure near uniform distribution. Replication builds on the ring to provide failover and strong consistencies via quorum. The algorithm is everywhere. Memcached, Cassandra, DynamoDB, Redis Cluster, CDNs. When your platform needs it, you'll recognize the problem and know the solution. I'm Fleshed Out Thoughts. I'm building a full-stack e-commerce platform for digital products and software services with Next.js and Supabase. If you're thinking through distributed systems, caching strategies, or when to introduce complexity, reach out. I'm open to freelance projects and consulting. The full post is linked in the description below. Next in this series, data management, how I classify data sensitivity, enforce retention policies, and handle right to erasure. I'll see you there.